Could this finally be the evidence we've been searching for? NASA's latest announcement has ignited excitement and debate among scientists and the public alike. A core sample drilled by the Perseverance rover from Mars's ancient Sapphire Canyon mudstone may be the most persuasive sign yet that life once thrived on the red planet. But here's the twist. It's still far from the smoking gun, and experts are quick to stress the ongoing uncertainty. The core, bored in July 2024 from the Chevaya Falls site in Neretva Valley, a once massive river that fed Jezero Crater's long-lost lake, showed features on Mars never before observed in such detail. Scientists studying the rock, which is now sealed for a possible future trip to Earth, found that its minerals and textures closely resemble biological fingerprints left behind by microbes on our own planet. Even so, the possibility of unknown chemical processes that don't involve life still looms over the find. This is the nearest we've come to detecting life on Mars, revealed Sean Duffy, NASA's acting administrator. Discovering a potential biosignature is a milestone that pushes the frontier of what we know about Mars and humanity's place in the cosmos. Duffy emphasized, though, that NASA will continue its rigorous standards and won't leap to conclusions as the agency pursues its ultimate goal, landing humans on Martian soil. Inside the Martian mudstone, the intrigue grows. The research team, led by Joel A. Hurwitz of Stony Brook University, describes a complex tapestry. Ultra-fine mudstone, punctuated with mottled reaction fronts, nicknamed leopard spots, and nodule clusters layered within the rock. Using sophisticated Sherlock and pixel instruments, Perseverance detected organic carbon, chemically bonded to phosphate, iron, and sulfur, in clearly repeated patterns. That level of organization, especially in such a harsh landscape, is striking. Two minerals took center stage: vivianite, an iron phosphate, and greigite, an iron sulfide. What's so special about them? Vivianite is often created when microbes in low oxygen, wet sediments chemically manipulate iron and trap phosphorus, forming blue-green nodules. Meanwhile, greigite is a signature mineral for environments where sulfate-reducing bacteria work in oxygen-starved mud. Experiments have demonstrated that greigite forms only when active microbes are present, never in sterile controls. And this is the part most people miss. Just because a mineral forms on Mars in patterns familiar from Earth's microbial life doesn't guarantee the same origin, but it certainly raises the possibility. Even more tantalizing, the way vivianite rims surround greigite-rich cores reproduces a bullseye pattern of electron transfer reactions found in some ancient Earth sediments. It's strong circumstantial evidence, though not direct proof of Martian metabolism. Scientists, exercising responsible caution, highlight that non-biological pathways could also explain these minerals, especially under Mars's unique conditions. So what is a biosignature really? It's a feature that might arise from living organisms, but more investigation is always needed to rule out lifeless sources. NASA guides these discoveries with the confidence of life detection, cold scale, a framework where each claim must first pass rigorous alternatives and contamination checks. Only once all possible non-biological explanations have been eliminated are scientists encouraged to declare life outright. For this Mars find, we are still early on that staircase. The chemistry is compelling, but not definite. Importantly, the researchers remind us that organic molecules can hitchhike to Mars aboard meteorites, or appear through purely chemical reactions in rocks, no biology necessary. Differentiating one from the other will require future laboratory studies, possibly right here on Earth, with the returned Martian samples. The details revealed a channel nearly a quarter-mile wide, evidence of lasting water flow into Jezero's primordial lake. The mudstone's low magnesium and manganese profile, along with its fine grain and absence of heat-altered minerals, strengthens the case that it preserves delicate signals that would otherwise have been erased by volcanic activity or high temperatures. The setting was, in theory, friendly to life as we understand it. But here's where it gets controversial. Are these complex chemical patterns telltale remnants of ancient Martian microbes, or merely the product of exotic, still unfamiliar geological processes? Some researchers argue that without more evidence, Occam's razor tilts toward the lifeless explanation. Nikki Fox, NASA's Associate Administrator for the Science Mission Directorate, addressed the growing excitement and skepticism. Let's be clear, this isn't actual life we're seeing. Rather, it's a possible biosignature, the strongest yet on Mars, but still a long way from confirmation, she said. Hurwitz agreed, underscoring the caution scientists must take to avoid false alarms. Duffy, though, was upbeat. It just might be the clearest sign yet that Mars once supported life. What would it mean if these minerals really do stem from microbial metabolisms? It would suggest that at least during a key window in Mars's history, surface waters provided the same energy strategies used by some microorganisms on Earth even today. If, on the other hand, non-biological processes are responsible, then the find still documents sophisticated redox, electron exchange cycles of iron, sulfur, and phosphorus, processes that shape the Martian crust with or without life. Either way, this discovery is a window into a different Mars, one where the landscape transformed, layer by layer, as the planet's climate and chemistry changed over time. Future studies might turn up isotopic signatures or powder-fine microtextures that conclusively separate living processes from lifeless ones. Until then, the best science is careful, collaborative, and open to surprises. The Perseverance team is already mapping where these potential biosignatures cluster and how they relate to other ancient rocks. Back on Earth, scientists are preparing a suite of new laboratory experiments, both comparing Martian finds to biological and abiotic reactions on Earth, and examining isotope ratios that living things tend to change in predictable ways. All of this hinges on the safe, clean return of Martian samples, a challenge still ahead. Pixel and Sherlock, with their ability to pair elemental and molecular maps, have provided a framework that's guiding the next wave of exploration. As the rover pushes onward, NASA's cold framework will help the community communicate findings without jumping to unsupported conclusions. Getting it right is more important than being first. Now, over to you. Do you believe these clues point to ancient Martian life, or are they merely an uncanny trick of geochemistry? Where do you stand, skeptic or believer? What evidence would it take to convince you one way or the other? Drop your thoughts in the comments. This is a debate with cosmic stakes.